Mark Twain sat on the deck of a river steamboat. As the paddle wheel turned, a point on the paddle blade moved in such a way that its distance d from the water's surface was a sinusoidal function of time. When his stopwatch read 4 seconds, the point was at its highest 16 feet above water's surface. The wheel's diameter was 18 feet and it completed a revolution every 10 seconds. Okay, so the first part is to sketch the graph of the sinusoid. This is a graph we're going to use, and we're going to label y as the distance from the water surface. The x, well actually we're going to just label t-axis because that's the time in seconds. Okay, now what else do we have here? We also want to draw a circle, okay, because we're going to need this periodic circle to understand how to plot it on the ty plane. So notice it said that the diameter is 18 feet. Okay, so altogether this is going to be 18. So imagine that this is the paddle wheel. All right, this is the paddle blade, exactly, paddle blade. Diameter is 18 feet. However, it says that the point was at its highest 16 feet above the water surface, right? So this paddle blade rises a maximum of 16 feet above the water surface. That means that since the diameter is 18, that means we have 2 feet of this diameter that is not visible. That means it's underwater, right? So if I paint it, it's going to be something like this, right? So this is 2 meters, 2 feet, 2 feet, and this is going to be 16 feet. Okay, so the rest of it, from here to here, will be 16. Okay, and from here to here, it's going to be the remaining 2. Okay, so that means we can go ahead and start. So 4 seconds. At 4 seconds of time t, the distance y is going to be 16. Okay, so we can label this graph as 1, 2, 1, 2, 3, 4. Suppose this is 4. And this should be 16 being max, right? So we can label this as 5, 10, 15, 20, right? So we're not going to need that much, but basically where the time will read 4 seconds, the distance from the water surface will be 16, and that's going to be the maximum. All right, that's 17.5, so 16 I would say is like right there. Right, so that's the maximum point. Okay. Now, it says that the revolution is every 10 seconds. All right, every 10 seconds is the revolution. So what does that tell us? That tells me that 5 seconds is exactly half the period, right? Because 5 is half of 10. So 10 seconds is a full sinusoidal wave. It's 10 seconds, and 5 seconds is exactly half of it. All right, so if we're talking about 4 seconds being the maximum, if we count 5 seconds from the maximum, we should, 5 seconds from the maximum, we should count 9 seconds as being, where the smallest point is, right? The lowest point. And likely that should be underwater already, right? Because here the lowest point is underwater to 2 feet, right? So it's going to be 5, 6, 7, 8, 9. All right, so that will be 2 feet below water, right? This is about 2.5, so I should say like right here. Okay, so, and also 5 seconds, so 2.5 seconds would be another point that we should find out, right? But that would be where the midline is, and that we'll find that out by using the algebra in part D to find the equation. All right, so we know that also 10 seconds ago from 9 seconds will also be the lowest point, that same lowest point, and 10 seconds behind will be actually extended to the negative t-axis. So basically when there's a -1 second, I know it sounds weird, you're never going to count -1 in time, but theoretically, if you were to start the wave, it would be here, right? That will be the lowest point. However, you're not going to start the wave here because it would look like a cosine, right? Because cosine starts from the lowest and goes back to the lowest when you have the full period, right? But the sinusoidal usually starts, it goes up by the magnitude, then goes back down, goes down by the magnitude, and then goes back up again to the midline, all right? So it starts from the midline, right? The sinusoidal wave, no matter the direction. The cosinusoidal wave starts not from the midline, either the highest point or the lowest point, depending on the where it opens. So we're not going to make it a cosinusoidal because we're asked to find the sinusoid, right? So the sinusoid function will begin normally halfway between the -1 second and 4 seconds. And how many seconds would that be? Right? That would be right in the middle. And we're going to find that out by finding the midline. Okay, so first, we already found the lowest and highest points. Let's also find the equation. All right, so the equation is going to be the sine form, which is written as A sine B x minus C plus D. Okay, first let's find the A, that's the amplitude. I'm using the absolute value just in case, because we know that sometimes graphs are upside down, but here it's going to be normal orientation for the sinusoid, so A will be the same thing as the absolute value of A, but I'm just being, pragmatic just in case if you need to understand that the absolute value is just the distance, no matter upside down or regular orientation you are of any sinusoidal function. Right, so it's going to be exactly the distance, right? And how do you find the distance? It's half the distance from the lowest to the highest points, right? And the lowest to the highest points is exactly the diameter, 18/2. The diameter divided by 2, right, is equal to 9. So the the true value of A is also 9 because we're starting normally up and not down. We're not upside down, but we're normal orientation, so A is also 9. Okay, it's not -9. Right, so now let's find the B. To find the B, we use the period 2 pi divided by B and set it equal to the period. The period here is exactly 10 seconds, right? So you set it equal to 10. Now solving for B, just replace 10 in the B. That means 2 pi divided by 10 is B, which is pi over 5 if you reduce the fraction. Right, now let's find the C. Is there a shift, a horizontal shift, that is? Yes, there is. Yes, there is. Okay. We know we need to find the midpoint, right? The midpoint between 4 and -1, right? And that will be the x value in which the sinusoidal function will begin right at the midline, right? So we need to find the midpoint to find that x value. So the midpoint between 4 and -1. So how do you do that? You just do 4 plus -1 and dividing it by 2, right? That's to find the average. This is the average formula. Even if it's negative, the average formula still works, even though this point is -1, right? So that will be 3 divided by 2, which is 1.5. Okay, so basically what that tells me is that it's going to be a positive 1.5 shift for this, okay? Because we're moving the beginning of the sinusoidal function exactly 1.5 units from the normal origin that we used to seeing, right? when the x value is 0, that's the parent function for the sinusoid. However, here we're starting from the 1.5x value, right? So we're moving it, so the c value is 1.5. It's positive because we're moving the graph to the right side. Speaking of horizontal shift. Now the vertical shift is, the d is responsible for that. All right, so the vertical shift will determine the midline, where that is, right? Because normally for parent sine function, the midline is the t-axis, where the y value is 0, right? But in this case, the midline is shifted up. It's exactly halfway between the lowest and the highest points. But you have to be careful when you're thinking of the lowest and the highest, because you can just subtract 9 from 16 to find that shift, to find the midline, right? And that will give you 7. And why is that? Why is that? Is because this is the highest point. You're subtracting the a value because you know the midline is going to be exactly the amplitude distance from the highest point. Right? So once you do that, you will exactly find the distance from the t-axis to the midline. Right? So that will be 7. Okay, so now our graph becomes 9 sine pi over 5 x minus 1.5 plus 7, right? So that's going to be precisely the graph that we found. Oh, actually, I should have replaced this with a t. I don't know why I kept it. I don't know why I put an x there. This should have been a t because we're using t-axis in terms of time, right? So just going to replace that with a t. All right, t. Okay, so now that we found it, we can go ahead and answer the other questions. Okay. Also, let's plot the midline. So the midline is at 7. So that will be 7.5. So I would say like right below it somewhere. It's not going to be exact, but you get the picture. This is going to be d is equal to 7, right? That's the midline. And we know the x value of that midline is what? It's going to be the c value, 1.5, right? If this is 1, 1.5 is going to be exactly there. So we're talking about this being the point. And 1.5 further from 4, that would be what? 5, 6.5. Right, 6.5 should be at the midline as well, right? So that will be your sinusoidal function. However, we want to start from here so as to make it look like a sinusoidal rather than a cosinusoidal, right? But basically, you just extend it until it returns to the midline. Okay. All right. So now that we have that, we can answer other questions. So the next question says what? It says, how far above the surface was the point when Mark's stopwatch read 5 seconds, 17 seconds? That's fairly easy. You just have to plot t is equal to 5 into this, okay? Into this y equation that we found. So it's going to be 5 minus 1.5, then plus 7. So if you do this right, this should give you 3.5. Okay, but so 3.5 times pi divided by 5, and then find the sine of that. Make sure you're in the radian mode, of course. Find sine of that multiplied by 9, and add the 7 after that in your calculator. You should get something like this, 14.3 feet. All right, and it makes sense here, right? Because if this is 5, 14.3 makes sense with this position, right? It's below 15, as you can see, but above 12.5, right? So it makes sense with being about 14.3. All right, the next one is about finding at 17 seconds. So you set t is equal to 17 into the y, substitute it into the t here, replace that with 17 instead of 5, and then work it out using algebra. All right, so this should give you 15.5 times pi divided by 5. Take the sine of that result, make sure in the radian mode, take the sine of that, that result multiplied by 9, and then that result plus 7. So if you do this right, you should get something like 4.2 feet. Right? Notice that this goes way beyond our capabilities of finding the, of verifying this result as it turns out, but you can use the fact that the period is 10 seconds and just subtract 10 from 17, you should be at the same exact point. Speaking of the t, right? So if you subtract 10, that will be 7 seconds. So 7 seconds are on this graph, so that would be 5, 6, 7, right? So this is the point that we should have reached. Notice that it's below 5, right? This point is below 5 as it should be, but it's above 2.5, right? So between 5 and 2.5, exactly where the ballpark of 4.2 lies, right? So it makes sense that our answer is correct. Okay, so now the last part, part D, what does it say? It says, what is the first positive value of time at which the point was at the water surface? At that time, was it going into or coming out of the water? And explain. So notice the water surface is going to be exactly the t-axis, right? It's going to be the t-axis where the y value, the distance from the water surface, is 0, meaning that it's the surface itself, the water surface, right? So we want to find what? We want to find the first positive value, right? We want to find this value, precisely this value, okay? But not necessarily, right? Not necessarily that value. It could also be this value, right? We have to know where we are, okay? So how do we test that? Because notice that if we extend this all the way to here, so basically if the y value is 0 after the t is 0, that's also possible. And it looks like it could be that way from what I drew, but I'm not sure. So I'm going to test it. All right, I'm going to test it. But I want you to take a look at this very carefully, because from this picture, this is the instance at which the paddle blade is coming out of the water, right? Because we're moving counterclockwise, right? We're moving this way. So that's the first instance that you see it touch the water if the t value is greater than 0, right? So if you find, again, your y value of 0 when the t is greater than 0, that will be the first instance, right? Okay. And how do I know this is the beginning? Because stopwatch at 4 seconds gave us the maximum point. But we don't know what happens between the 0 seconds and 4 seconds on Mark Twain's stopwatch. It could be that this is the first instance at which the time is already positive when the y value is 0. Right? So we have to test this point first as being the first, and then this possibly the second. Okay? So let's test that. How do we do this? We set this function to 0, right? Because we want to test the y value of 0 and find the t values that correspond to these two. All right, so now let's do that. So it's going to be 9 sine, which is copying the right side. Notice the t is unknown because we already know the y, and we have to solve for the t value. So we leave it like this. Okay? And now how do we do this? We subtract the 7, and then we divide that by 9. So it's going to be basically negative 7 over 9 as a result of subtracting 7, and then dividing it by 9 both sides. We get negative 7 over 9 is equal to sine pi over 5 times t minus 1.5. Okay? So now how do you get rid of the sign? Never divide by sign. That's not how it works. You have to take the arc sine of both sides. So what that means is you can say that pi over 5 times t minus 1.5 is equal to the arc sine of the other side. Okay, the arc sine of the negative 7 over 9. Okay? So now we just have to distribute this. Pi over 5t minus 1.5 being multiplied to pi over 5 should be set equal to arc sine of negative 7 over 9. Okay? So notice that you can solve for t this way okay? Because first you're going to add the 1.5 times pi over 5, the product to the right side of this. So you're going to say arc sine of negative 7 over 9 plus 1.5 times pi over 5. Okay? And again, I don't know what this result is going to prove. And also notice that when you solve finally for t, when you add this to the right side by adding what we just did, you also have to multiply this by the reciprocal to make it a 1t, because you're solving for 1t for t. Right? So you have to multiply this whole thing after you add this product by 5 over pi, the reciprocal, 5 over pi. All right? So now let's test that and see if the calculator answer, which gives us this, this angle, and notice it's going to be in quadrant 4, right? Because if we make this like that, it's going to be in quadrant 4, and that's what the calculator would give you, the quadrant 4 value of that angle for which the sine is negative 7 over 9. All right? So notice that this would be the calculator. So let's test that. Let's test that if that gives us the positive t value greater than 0, because if it does, that's going to be the angle that we could use. So notice that if you solve this using your calculator, be very careful that you're in radian mode, of course, because you're dealing with pi's. You should get 0.08 seconds. What that tells me is that it's definitely a positive value. It's nearly 0. It's really, really close, but it's still positive. And that matches what I drew here, because the y value of 0 is where the t value is barely positive, right? It passes the origin, kind of, right, as you can see. So it is positive. So that means we're not going to solve for that other angle using special formula to find the second angle. We're good with this angle, because that's the first instance, because that's the first positive value of time at which the point was at the water surface. Now, how do we know which direction? It says, is it going into or coming out? Well, obviously, if it's going up, right, the distance from the water surface increases. That means that the paddle blade is coming out of the water, right? It's coming out of the water and it's going in right here, back in the water, right? So it's coming out. Coming out of the water.